Today we're going to cover 2.1 from our book. This is a section about direction fields. In this section, we still do not know how to solve a differential equation. And so what we're going to do is examine how maybe we could see the way that a solution behaves, given that we know what our first order differential equation looks like. Okay? So any derivative that we have, if we were to solve for dy dx and get it in terms of x and y, then what it's giving us is slopes of tangent lines to the solution curve. So I've got this differential equation right here, dy dx is equal to x over y. This tells me that the way that the slopes of the tangent lines to my solution look is that they are x over y. So I could plug in any x and y pair and figure out what the slope is at that particular point. And that's our main idea, because if we can find the slope at that particular point, then we can graph like an itty bitty line to represent the slope of the solution at that specific point. So the dy dx gives us some function that represents the slope of the tangent line to the solution without actually giving us the solution. And if we pick an xy value, then we can figure out what that slope value is as a number. Okay? If we can find that slope value as a number, then we can draw itty bitty tangent lines. These are also called lineal elements. You'll see the word lineal elements in some of your homework. And we could draw them on a graph, and then we would be able to see what's kind of the flow of a possible solution curve is, because a tangent line, by definition, runs parallel to the curve of the solution function. So we're going to try it. We're going to pick several quote-unquote good points and calculate dy dx at those points, and then draw tiny little tangent lines at those points. Our particular differential equation is dy dx is equal to the square root of xy. And so I want to pick different xy values and plug them in and see what happens. Before I go anywhere with this, though, what I should do is get an xy axis drawn on here, because I just have kind of generic graph paper drawn on here. So I'm going to get an xy axis, and then I'll mark it up. This will be 1, 2, 3, 4. So every 2 boxes will represent a movement of 1 unit. I don't want to use every box, because then I get this itty bitty graph and I can't really see anything in it. So bigger is better for seeing. Okay. Now, there are a lot of points on an xy axis, and we need to make sure we're picking wise ones. So for example, I probably should not pick the point -1 with 1. What's the problem with that one? Well, if I have x is -1 and y is 1, then I'm taking the square root of -1, which is not a real number. So let's not do that. Let's erase all that and stick with good values. So first thing we know right here is that the product of x and y must be greater than or equal to 0. Okay? All right. So we have to pick from the first quadrant and the second quadrant. We can choose from the axes. That is okay. So I'm going to choose something on each of the axes first. How about if x is 1 and y is 0? Well, then we're going to get the square root of 0, which is 0. What this is saying is that on the x-axis at the point 1, 0, we have a slope of 0. So I'm going to draw an itty bitty tangent line at that point. In fact, this is going to happen if x is 2 and y is 0 as well, because that product will again give us 0. So I can continue along here, and you can see how we're getting a bunch of these for free right now. It happens to be that if x is negative, this still works, because y is still 0. So if I have -1 for x and y is 0, I still get a 0 slope. And this goes on and on and on. Okay, so this is allowing me to get a bunch of freebies, but they're kind of boring, right? They all have a zero slope. It's just a horizontal lineal element along the whole x-axis. Let's look at what if x was 0 and y was 1. Well, the same thing's going to happen because one of the numbers is 0, the product will be 0. So the slope is 0. That means when I go to the y-axis, any of the y values plugged in is non-zero while x is 0, it's going to give me a 0 slope. So on the y-axis, I again have horizontal lineal elements or tangent lines. So I'll just go up and down the whole y-axis doing this. My hope is that you trust me on this. Anytime one of the variables is 0, the overall slope will be 0. Okay, now we get into the nitty-gritty where it's a little bit more complicated. Let's say that x is 1 and y is 1. It's kind of boring, but it's a good one to work with. We get the square root of 1, which is 1. So at the point 1, 1, which is right here, the slope is 1. Okay? Let's say if I went to 2, 2, oops. At 2, 2, I get the square root of 4, which is 2. So I'm going to go to the point 2, 2. Now my slope is greater. So there's more of a slant to it than there was at 1, 1. And something similar will happen at 3, 3 and 4, 4. Okay, so things are not the same, but maybe I should get a little bit more creative here. One of the things that's also true is whether I did 1, 1 or negative 1, negative 1, I got the square root of 1, which is 1. And so I can also go down here and have the point negative 1 with negative 1 has a lineal element with a slope of 1. Similarly, if I'd plugged in negative 2 and negative 2, I'd still get the square root of 4, which is 2. So again, I'll get another point in there, but it has a steeper slope. Okay? All right, now I want to do something kind of different. Like, what if the point was, I'd like nice numbers, but I'm going to go out on a limb and say, let's do 2 with 1. So 2 comma 1. Well, then I'm going to get the square root of 2, which is approximately 1.4. And I go over to the point 2 with 1. I draw my point. 1.4 is steeper than 1, but not as steep as 2. That's pretty hard to draw. You may be recognizing right about now that this is not something you want to do a lot by hand. But that's okay. We gotta practice it anyway. A similar thing will happen if we were to look at negative 2 with negative 1. We would also get the square root of 2, which is about 1.4. So I'll go and I'll put that point in there. It will be more steep than the slope of 1, but less steep than the slope of 2. It's, again, really hard for me to draw that. Hopefully you get the point there, though. We could also look at other points. We could go big and say, let's look at the point 3 with 4. So now we get the square root of 12, which is unknown to me right now. It's bigger than 3, smaller than 4. So I'm pulling out my calculator right now to just give me a decimal approximation of about 3.5. It's 3.464101615. 3.5 is close enough. So I go to the point 3 with 4, and I have a wicked steep slope. Like, trying to draw it, it's almost vertical. Okay. Similarly, if I had plugged in negative 3 with negative 4, I'd also get square root of 12. So let's go to negative 3 with negative 4. And again, I have a super steep slope. Okay. my hope is that this exercise just showed you that we can't actually get a lot by doing this by hand. But on a test, you may be asked to just come up with a few of the lineal elements for a direction field, and this is what we did. This was just drawing a few lineal elements for a direction field. We cannot possibly draw a complete direction field by hand accurately. And so we need some sort of technology to do this. And so the other thing is that, for example, this ODE dy dx is equal to the square root of xy. We can solve this, but we don't know how to yet. And so maybe we could just learn something about the solution by looking at the direction field. And so that's kind of our goal, is that we could look at a direction field and we could talk about the flow of our solution. And that's about it. So I already have a graph pulled up, and if you're following along with the notes that are printed out, then you already have a graph as well. Otherwise, if you're on a computer and kind of just watching, you can click on one of these links that I've put in here. I clicked on GeoGebra for the link that I have, and I've also got one for CalcPlot3D to give you a direction field graph as well. You decide what you want to use. So again, I'm using GeoGebra, and in GeoGebra, a lot of this was kind of like there was already something populated. They had a particular differential equation, and they've written it as f prime of xy to indicate dy dx. Kind of incorrect notation, but we'll take it. It's fine. And so I put in the square root of xy, and I put a boundary from -2 to 2 and -2 to 2 for x and y. And it gave me this direction field here, which kind of aligns with what I was starting to draw on the previous page, but I never would have come up with in this lifetime. So I could look at this and I could say, it looks like if these are lineal elements and each one is supposed to be tangent to my solution curve, then if I was to start out somewhere on this graph and try to draw what a solution looks like, it might just follow along this flow, right? I could go in here and try to draw any curves and just make sure that they're ending up so that they are tangent to the lineal elements. And we're not going to do this perfect. That's not the point. The point is actually to just get comfortable with what it is that we're doing. That's it. Again, the idea is that you might not be able to solve the first order differential equation you're given, but you could draw its direction field or use a computer to get a direction field, and then you could sketch some curves on it, and you could see like, oh, okay, well, that's what it looks like. All right. So keep that in mind, and I've given you a program that you can use. You can use it all you want to come up with the direction field graphs, but I would say make sure to print one out and practice drawing curves through it, okay? On a test, you could be given a direction field and asked to draw some of the possible solution curves on that direction field. Okay. Let's see. So I'm kind of going through this. I've already drawn some sample solution curves, but what if we were given an initial value? And in particular, what if we were given the initial value 1, 1? Okay, well, if it's 1, 1, then it has to exist in the first quadrant, not in the second one, and it's going through right here at 1, 1. So I'm going to extend below and above, trying to reach out to where I would hit the lineal elements in such a way that they run tangent to those lineal elements. And this would be an example. Again, it might not be perfect, and that's totally fine, okay? And we could draw a few more. We could, try some more. Let's say, what if the point was, oh, I don't know, -1, -1.5. Go down here, and then I would try to extend from here, always making sure that as I extend, if I hit a lineal element, I pass by it in a tangent way, okay? Now, if we were given like a particular initial value, we could say, we've drawn all these curves. We could pick one of these curves and we can say, well, this is the solution. So if you go back to the direction field and you open this up in GeoGebra, there's an option for you to get some solution curves. So let's just go back and see where on the bottom left it says solution A, solution B, solution C, solution D. So you could click on those and you could get some particular initial values, and I've done that and printed it on here. So I've put in 1, 1 as an initial value, and I can see my solution curve. And then the others were just kind of generated, so they're decimals. They're pretty ugly, but it gives us the right idea. The point is to notice each of the curves that are drawn here in green on this black and white direction field. Each of these curves, as they extend from the initial value, when they hit a lineal element or pass nearby one, they are doing so in a tangent manner. They do not just cut across a lineal element. That will never happen. So that we're seeing the flow of the solution when we see the picture of the direction field. All right, got some examples. And with each one of these examples, I'm giving a differential equation that we can't solve and several possible initial values. And our job is to plot the initial value and then do our best to get a solution curve and its flow on the graph, okay? So the first one, A, is y of -6 is 1. So that's x is -6, y is 1. That's going to be right about here. I should not use blue because the graph is in blue. Okay, I'll use green. Okay, so if I extend from the initial value and I make sure that as I extend, my graph is always running parallel to the lineal elements, I get a picture something like that. If I then go to, okay, let me label this. This is A. If I go to B, y of 0 is 1. That means when x is 0, y is 1. So that's going on the y-axis. And so I'm going to extend from the y-axis. And as I come to lineal elements, I'm going to make sure that I don't cross them. I just run parallel to them. So that's going to the right. Now going to the left, I draw, and as I come to lineal elements, again, I'm trying to make sure that I keep running parallel to my lineal elements. We're not trying to make them be on the lineal elements, just to follow the flow, okay? And so this works for B. It's approximate, it's not perfect, and that's okay. The next one for C is y of 0 is -4. So that's down over here. When x is 0, y is -4. And again, I'm going to extend to the right. Things seem to just be going kind of straight up and to the right until there's a little bit of curvature in the far right in the first quadrant. And then when I extend to the left, it looks like my graph is going to start to veer downwards. Okay, that's what we got. Last one, that was C, sorry. The last one is D, and that one says that y of 8 is -4. So when x is 8, y is -4. So that's about down here. And this one's interesting. So I can really only go to the left. Because on the right, I run out of graph. And so this is good enough. And this is what I'm talking about. Like on a test, you might be given a direction field like this, where you have to draw the possible solution curves given that you have an initial value. Okay. It's not perfect. It's not meant to be an exact science. It's meant to just follow the idea behind what we're doing, which is following the flow of a direction field to get what a solution curve might look like. The second one I have, and I believe it's the last one. Yeah. Okay, in this one, we're supposed to draw solution curves that go through the indicated points. The differential equation is dy dx equals sine of x cosine of y. I want to mention this because I forgot to mention it on the previous problem. I never once actually considered what the differential equation was. I stated it, but I didn't care what it was. I have a picture of what the first derivative looks like at all the particular values on this graph. I have little itty bitty lineal elements that tell me the numerical value of the slope at any given point on the graph. That's all I care about it for. And since a computer generated the direction field, I'm done with the differential equation. Now I'm using the graph to give me the possible solution to that differential equation, given that I have an initial value. So let's go with that initial value. We've got y of 0 is 1. So it means when x is 0, y is 1. We're here. Okay, this one's always a little hard for me. So to the right, it looks like my graph is going ever so slightly upward. But then when I hit this kind of in the middle, I'm going towards something that seems to be kind of flattening out and then even starting to go down. Okay, so very slight slopes that are almost near zero. And again, to the left, we have a sort of similar situation here where the solution curve has a slope of near to zero. Okay. All right, let's look at, I'm sorry, this is A. B is y of 1 is 0. So now we'll go to x is 1, y is 0, and see what we get. Okay, to the right, we head off in a positive slope direction. And as we come to the lineal elements, make sure to stay parallel to them. And there's our curve there. And then to the left, we're going to go, looks like our slope is leveling off to near zero. But then it is picking up again. Now we have a negative slope. And then it's leveling off to zero again and going towards a positive slope. So very symmetric. I have to admit, I accidentally almost got that symmetric. These are really hard to draw. It's not about perfection again, okay? But we should see some sort of symmetry in our solution curve, given that the flow of the direction field is quite symmetric, okay? All right, another one is, oh wait, let me label that. That was B. Another one will be C. Y of 3 is 3. So there's x is 3 with y is 3. Here we go. Okay, to the right, we don't have far to go. And to the left, let me start that over. It's always hard for me to draw from right to left. So I'm kind of assuming something's happening here above my actual graph because of the symmetry. I'm a little bit off. It's okay. I have the general flow there. It's like a sinusoidal curve. Okay, so this was C. And then D, need a different color. Let's see. Let's go with a dark green. Okay, y of 0 is -5/2. That is a -2.5, which is down about here on the y-axis. Okay, I'm going to go the left first, do the hard part first. So again, I'm just following the slopes of these little lineal elements. To get the flow of my solution curve, and then I'll do it again. It's almost kind of cathartic in a way. You know, you're not doing anything hard. There's no problem to solve. You're just drawing a curve to follow a flow. That's it. Okay. When it comes to WebAssign homework, you will be given graphs and you will be doing multiple choice. I recommend that you give yourself half a chance so that you're really learning this and not just eliminating choices. Forget about the multiple choices. Take the differential equation, plug it into GeoGebra, print out a direction field and practice. Just practice filling in some of the solution curves and then compare it to what you have on WebAssign. I know that that's more work, but that's where, that's the important work. That's really understanding what you're doing and not just eliminating the worst choices so you can say that, oh, what's left over is the answer. Okay, so that's it for direction fields. Again, if you have any questions at all, do not hesitate to reach out.